Welcome back to Home Learning. The subject today is computer science, and the topic that we're looking at is searching algorithms. We're going to go straight over to Mr. Holton, who's going to explain what searching algorithms are, and then you'll have a task and some exam questions, both reviewed by Mr. Barnes. So over to Mr. Holton.
You probably ask a computer to do a search for you every day, whether it's on the internet or if it's looking for files or something like that, then you are probably asking the computer to do a search. And there's a few different ways that a computer can do this. Actually, something like Google is really complex. It's a really complex algorithm, really complex sequence of steps that it goes through. But we're going to go through a couple of simple searching algorithms that you'll need to know. First one is called linear search. This is a very straightforward algorithm. It's the kind of search that you might do if I gave you a pack of cards in a random order and I said look for the 6 of diamonds or something like that. In that, if I give you a random set of numbers like these ones here and I said okay, we're going to look for the number 12, what the computer would do is first check the first one in the list, so that's number 7, and ask is it 12? Well, no, it's not, so I'm going to move on to the next one in the list. It's 10. Is that 12? No. So I'm going to move to the next one into the list. Is that one 12? And so on until it finds the number that we're looking for. This works on letters as well as numbers, or anything really that you can put into any sort of order. So if I'm looking for the letter F here, then I go through exactly the same process. Ask the question, is this F? No. So I go to the next one and so on and so on. And that's fairly straightforward. That's one of the easiest searching algorithms that we have. A little bit more complicated but much more efficient is something called a binary search. So we're going to go through that as well. Now there's a big problem with binary searches. Even though they are really efficient, they're very, very quick, the data that you're searching has to be in order. If it isn't in order, then the whole thing doesn't work. So let me give you a sequence of numbers in order and we'll see how it plays out. What happens is this. I look for the midpoint. So I've got 1, 2, 3, 4, 5 numbers in this list, which means the middle one is the third number here, 46. So far, so good. And then let's say I'm trying to find the number 39. Always got to bear in mind exactly what we're looking for. So I'm trying to find the number 39. I ask myself, right, have I found 39? Is it in the midpoint? Well, no. 39 is not 46, so I've not found it. Okay, but 39 is less than 46, and I know these numbers are in order, which means I can eliminate the half of the list that 39 isn't in. And then straight away I've got rid of half my data. Then I repeat the same process in the numbers which are remaining. So I've got 14 and 39 here. If I've got an even number, then what I tend to do is find the midpoint and round up. So the midpoint would actually be, if I've got 2 elements here, it would be here, wouldn't it? It would be like 1.5. But I round up to 39, okay? So I round up to this element here. And ask myself, does that equal 39? Yes, it does. So I found the element, okay? One of the key things about binary searches is that they are really efficient. So let me show you what I mean by that. So let me give you a big list of letters. Again, this has to be in order. And to save you counting, I'm going to say we've got 11 letters here. Let's say I'm looking for the letter Q. So the first thing that I do is check for the midpoint. So the midpoint is here, K, because I've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 letters on either side. I know that's definitely the midpoint. And I'm asking myself, is Q equal to K? Well, no, it's not, is it? But I know that Q is greater than K because it comes later than in the alphabet. And I can eliminate the half of the list that K is not in. So there it goes. And then I've got a new list, 1, 2, 3, 4, 5 elements in it. New midpoint there, that's P. And then I'm asking the same question, is Q equal to P? Well, no, it's not. So I'm eliminating half the list that it's not in. I go through the same process once more here because I'm rounding up. Is it equal to W? No, I'm eliminating the half of the list that it's not in. And then sure enough, I found it here. Okay. I have done that in 1, 2, 3, 4 steps to find Q in a binary search. If I had a linear search, if you think about it, it would take many more steps because I'd have to do A, C, E. Let's count them. I'd have to keep going all the way until I found Q here. So if we're comparing the two, binary can find something in 4 steps, whereas linear would have to do 10 steps to be able to find it. So a binary search is much more efficient. But the big drawback for binary searches is that the data has to be in order. And if you look at sorting algorithms, that's not a quick and easy thing to do. That's all you need to know.
Okay, so now you've heard all about how searching algorithms work, you're going to go and complete the first task. You've got 10 minutes to complete the task. Off you go. And that is time up. Hopefully you managed to finish in that time. We're going to review answers now with Mr. Barnes.
Okay, so you should have just completed a quiz about the linear and binary searches, and in there you would have come across two algorithms. Now, those quizzes are self-marking, so please do have a look at the correct answers. However, I think it's worth going through how the algorithms actually work, because as well as being able to do a linear or a binary search yourself, you may be given the algorithm and asked to explain certain parts. Okay, so here we've got a function for the linear search. Now it may or may not be written as a function, but we've got two pieces of information being passed into it. So we've got the search item. This is the item that we're searching for. And we've got the search list. So this is the list of items that you're looking through. So the search index is the index, the item that's going to be checked. And we start that at 0 because anything in a list or an array will start at 0. And what we've got here is a loop. Okay, so we've got iteration. And this loop is basically saying while the search index number is less than the length of the search list. So if the search list had 8 items in it, len search list would return 8. So whilst the search index is less than the length. So then what it does is it checks if, and remember with an if statement, this is selection. Okay, if the search list, and then in the brackets the search index value, so this is a list, we are pulling out one piece of information from it. So if it's the first time through, we will pull out what is in element 0, or the first element. Okay, so it's going to take that value, put it in there, and it says if it equals the search item, then return true. And what that means is we have found that item exists. Okay, now there is no else to the if statement, and that's fine. And after that, we've got this thing here, search index equals search index plus 1. So this is what we call an incrementer. So it increments by 1. So if search index was at 0, because we were checking the first item, it then adds 1 to it, so it becomes 1. And then we've got the end while. So we go back to line 3, where our while loop starts, and now the search index is 1. We say while 1 is less than the length. So as long as the length is more than that, we go again and go again and go again. We do that until it gets to the end of the list. And at that point, it will return false if we haven't already returned true, because we've checked the whole list and that means nothing has been found. So we've got some key things in there. We've got some iteration, which will repeat, moving its way through the loop. We've got len, which checks the length of the list. We use selection to see if the current item being checked is the one we're looking for, and we've got a value that gets, or a variable that gets incremented each time by 1 so that we can look at the next item. Okay, so let's have a little look at how the binary search works now and how the algorithm works for it. This is a little bit more complex than linear search, and the easiest way to understand this is by following through this algorithm using some data. Okay, so first of all, at the start, we've got two parameters that go into the function. The search list, which is here, 4, 6, 8, 9, 10, and 12, and search item, and I'm looking for the item number 10. Okay, so we've got, first of all, the start point. The first time through, the start point is going to be 0, because with any list, the first element in an array is 0. Okay, so, and our endpoint is going to be the length of that search list. So this will find the length, and the length of my list is 6. Sorry. Okay. So whilst the start is not equal to the end, so this is iteration again because we're going to have to repeat the process. And whilst the start value and the end values are not the same, keep doing this. The first thing we need to do then is find the midpoint. So this is achieved by adding the start to the end and then using the div operator by 2. So our start is 0, our end is 6. So it do 0 plus 6, which is 6, div 2, and that will give 3 because it takes the whole part of the division. Okay, so now we've got our midpoint. So next we say if the search list and element midpoint. So what we're basically doing is we're taking that number 3 and we're going to put it in there. So if the search list element 3, which is this one here, the number 9, is greater than the search item. So is number 9 greater than what we're looking for? Number 10? No. So we skip and go to the else if. Now we check if that item, number 9, is less than the search item, which it is. So what we do there is we set the start value to the midpoint plus 1. because what we're basically saying now is we don't need to check 0, 1, 2 because we know it's in order. 3 is less than it, so we're basically saying get rid of all of that, and our start point next time is going to be element 4. So we get to the end while, we go back round, while the start is not equal to the end. Well, the end hasn't changed, so that stays as 6. So start is 4, end is 6. It has not changed. They are not equal, so we go on. Midpoint equals start plus end divided by 2. So start plus end, 4 plus 6 is 10. Div 2, so 10 divided by 2 is 5, remainder 0. So the remainder doesn't matter anyway, so our midpoint is now number 5. And we do the same again. If the search list midpoint, which is element 5, which is the number 12, is greater than the search item. Okay, so it is greater than the search item. 12 is greater than 10, so the end point becomes the midpoint minus 1. Okay, so the midpoint minus 1 is 4. When we go back round, we do midpoint equals start plus end. 4 plus 4 is 8, div 2. My midpoint is 4. So if search list element 4, which is the number 10 this time, is greater than the search item. Well, it's not, so we go to the next one. Is it less than it? No, it's not. So is it the same as? Yes, it is. So it will return true because there is a match found.
Right, so it's time for an exam question. As ever, give it your very best shot and we will review these afterwards. You've got 10 minutes, off you go. And that is time up. So we're going to go over to Mr. Barnes. Please make sure that you self-assess your answers and you correct anything that you didn't get 100% accurately.
Okay, so let's have a little look and model these exam questions as part of our deliberate practice on searching algorithms. Okay, so first of all, we've got a sample of data shown in figure 4. Show the stages of a binary search to find the word zebra. So, first of all, we need to find how many items are in the list. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if there's 9, our middle item is the 5th item. So, I'm going to write middle item equals orange. Then I'm going to compare it to zebra. So orange less than zebra. And then I'm going to create my new list. So because orange is alphabetically less than zebra, I can get rid of all of them. So my new list becomes range, tent, wind, and zebra. I'm going to repeat that process. So my middle item now is in between tent and wind. So remember, we round up. So I'm going to put middle item equals wind. Wind less than zebra. New list. Because I've checked wind and I know it's before it, I can now get rid of wind, tent and range. So my new list is zebra. Match found. Okay, so let's have a little look at the mark scheme. So we've got here, if I just move it up, you get 1 point for comparing zebra to orange. So orange and zebra. Then another point for greater and split the right hand side. So yeah, I've checked that and my new list. Further comparison, so I've done the same again. And then correct identification using the method. Now, the reason it says 1 or 2 depending on choices made is because we always, if there's a missing, like the middle is nowhere, we always round up, but you can also round down. As long as you're consistent, it doesn't really matter. So, there we have it. 4 marks. Okay, let's have a look at the final 2 questions then. So, Sally's creating a list of all the places she wants to travel. Her top 5 are Australia, India, Greece, Tokyo, and South Africa. Show the stages of a linear search. Okay, when finding the word Tokyo. So, check first item. Australia. No. Check second item. So remember, with a linear search, you just work your way through. Check second item. India. No. Check third item. We've got Greece. No. Check fourth item. Tokyo. Match found. Okay, so linear search, you just work your way through. It's quite a repetitive process. So we check each item in turn. And then finally, we've got to explain why you'd not be able to perform a binary search on this data. Now, if you look carefully, you will notice that it is not in alphabetical order, because Greece should come before India and South Africa should come before Tokyo. And for a binary search, the data must be in order. So I'm going to write the items are not in alphabetical order and they must be for a binary search. Okay, so I'm just going to push this up a little bit. Oh, a bit too much. Okay, so let's look at the mark scheme. Just fold this over. Okay, so for 2A, 1 mark for each. Comparing Australia to Tokyo. Well, we've done that. Comparing the following values in the correct order. So India and Greece, 2 marks. Stopping once Tokyo has been found, 3 marks. And then finally, for why we cannot perform a binary search, the items are not in alphabetical order, 1 mark. There we go. Modelled answers.
Okay, and that's everything you need to know about searching algorithms for GCSE Computer Science. See you next time.